So what I'll take a look at today is the next section. This is on section 5.5, which is on zeros of polynomial functions. Okay, so I want to just do a little bit of kind of a reminder of what we did before break started. So remember, last thing we talked about was dividing polynomials. So remember, there were two techniques that we had to divide polynomials. One of them was long division, and the other one was synthetic division. So long division, that was just a very tried and true method that's going to work no matter what type of polynomials we're dividing by, and it mimics very much that idea of long division that you've done way back in the day, back in grade school. Now, synthetic division, that was a shortcut method, and that only worked when we were dividing by a linear term, like something, say, like x plus 2, or something like, say, x minus 5, or something like that. So synthetic division, that was a shortcut way that we only had certain numbers appear and with this little box, and we had this kind of repeated process. So we'll go through an example of synthetic division today in this video, but I at least wanted to kind of remind you of what we did before the break. So this was an example that we worked on before the break. We did division, where we did x cubed minus 6x squared minus x plus 30 over x plus 2. We did division, and what we got as a quotient was x squared minus 8x plus 15, and our remainder in this case was 0. So we just were able to write it using this notation. Now, we also noticed that if you multiply both sides by x plus 2, you would get this numerator here is equal to x plus 2 times this over here. And so what we noticed was that we've started to factor, right? Because remember, when we factor something, we're writing it as the product of two different things. Or we've never done this yet, or maybe you haven't done this yet, is to write it as more than two factors, or more than two things being multiplied together. So we've started to factor this. This isn't fully factored, but at least it's starting to be factored. And so what we recognize is that division, this can be a new factoring technique. At this point, maybe the only factoring techniques you know is to figure out what multiplies to the last term and adds to the middle term of a quadratic. Maybe you know something like factoring by grouping, but division is going to be a very nice way to do it. So before we get to an example of factoring, there's an important theorem that we need. And so this theorem is called the Factor Theorem. So the Factor Theorem states that if k is a 0 of f of x, so if it's a 0, remember, that is basically saying it's kind of like an x-intercept. It's where our function is going to equal 0, or the y value equals 0. This is going to be true if and only if x minus k is a factor of f of x. So that means that if we know a 0, then we know a factor. So if 5 is a 0, x minus 5 is a factor. If negative 3 is a 0, then x plus 3 is a factor. On the other hand, we also know that if, say, x minus 2 is a factor, then that means 2 is a 0. If x minus 7 is a factor, 7 is a 0. If x plus 1 is a factor, then negative 1 is a 0. Okay, now, in other words, though, another way to phrase this is saying that if we have this thing, f of k is equal to 0, so if we know the number that makes our function equal to 0, then that means x minus k is going to divide it. So this is one of the most common ways that we're going to be using this theorem in just one of the directions here. So if we find a number that makes our function equal to 0, we can say that x minus that number will divide it evenly with no remainder. So let's take a look at this example over here. So if we want to completely factor f of x is equal to x cubed plus 4x squared minus 4x minus 16, knowing that f of 2 is equal to 0. So we would like to use this factor theorem and use division as a technique. Yes, technically you can use other factoring techniques on this, but we'd like to just learn how do we work with division. Okay, so what we have for this is we have our factor theorem. So our factor theorem over here, it says that if k is a 0, if and only if x minus k is a factor. So a 0 we have is 2. So x equals 2 is a 0. That is a 0, makes our function equal to 0. So that means x minus 2 is a factor. So we see that since x equals 2 is a 0, what this implies is x minus 2 is a factor. So if it's a factor, what we're going to try to do is we're going to divide by it, right? Because we know that if we divide by a factor, we're going to have a remainder of 0. So we are going to be looking at the question of x cubed plus 4x squared minus 4x minus 16 divided by x minus 2. And we like to figure out what is that equal to. So to do this, this is where we have to use division like we did before the break. So in this case, we are going to, let's do synthetic division. It's going to be the fastest, quickest way to do this. So remember, so with synthetic division, we place a little box to the left. This box is going to contain a number. It's going to contain the number that makes the denominator equal to 0. So 2, if I plug in 2, that makes it equal to 0. So I plug into this. Now, up top, we're going to write the coefficients of whatever we are dividing into. So we have 1 is the coefficient of x cubed, we have 4, we have negative 4, and we have negative 16. Remember, if there's a term that's missing, so if there was no x squared term, we would write a 0 there. We can't skip spaces. We have to have every power of x. So if there's not one there, put a 0. And then underneath here, we put a little line. And so the first step that we do is we bring down this number. Then we multiply this number times this, and we get 2, and then we add. So remember, we had this acronym of MAMA, this idea of multiply, add, multiply, add, multiply, add, multiply, add. So we're going to, now that we've added, we're going to multiply, and then we add to get 8. We multiply, and then we add to get 0. Now remember, we did synthetic division. This forms our quotient. These are the coefficients of a quotient. This has degree 1 less than this. So this was a x cubed. This is going to be an x squared term. This last number is the remainder. This remainder always needs to be 0 if, indeed, we've done all of this correctly with the factor theorem. If you don't get 0, that means that that doesn't equally divide, so that probably means you made a mistake somewhere. So what this means is that this forms our quotient up here, so this becomes x squared plus 6x plus 8. So how we can write this now as a factoring problem is we can see how this begins to factor for us. That we have x cubed plus 4x squared minus 4x minus 16 is equal to x minus 2 times x squared plus 6x plus 8. So we simply multiply by the denominator and we get this. So again, this is the start of factoring, but we haven't completely factored it. Because when we look at this side, this term over here, this can be factored one step further. We have the ability to take this one more step. And so when we're looking at something that's going to be completely factored, we need to make sure that there's nothing left for us to factor. So here we look to see what multiplies to 8 and adds to 6. So this will be x plus 2 times x plus 4. And so this is now the fully factored form of x cubed plus 4x squared minus 4x minus 16. And so this would be the final answer that you are looking for. Now, if instead we were asked, what are all of the zeros? What are all of the zeros of this polynomial? Right? We could fully factor this, and this is our fully factored form. All of the zeros, remember, the zeros, these are if this was equal to 0. What x values make this equal to 0? So if this is fully factored, we could set each of these equal to 0. And so we would have the zeros would be 2, -2, and -4. So x equals 2 is a 0 because of this, x equals -2 is a 0 because of this, x equals -4 is a 0 because of this. So it just depends on what we're asked for. If we just want it factored, we want it like this. If we want all of the zeros of the polynomial, we'll fully factor it, and then we'll set each term equal to 0 to get the list of the x values.